Assalamualaikum. Good morning.
Morning, Doctor.
Apa semua?
Baik.
How are you guys? Kaifa haluk?
Alhamdulillah, Doctor.
Alhamdulillah.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala sayyidina Muhammadin asyrafil anbiya'i mursalin wa ala alihi washabbihi. Allahumma rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Okay, where is our last slide? I forgot. Slide number, Azizun. Slide number. You remind me, I can't remember. 29, 28. Where do we stop last time? 29.
29.
Okay, right. Thank you. Thank you, guys. Right, so I repeat again. Example 1.1 in page 24. Given a unity feedback system that has the forward path transfer functions, okay, as follow, which is here, right? So you are given three open loop poles, -2, -4, and -6. So when we multiply together, it becomes S cubic until plus 48. And we already plotted, sketch the root locus, okay, as shown here, okay. So I believe that you can plot using MATLAB. Then we are given a 10% overshoot spec design. So the 10% overshoot is given by the zeta 0.591, which can be determined using three approaches. The first one is using overshoot percentage. The second one is using a formula of zeta using natural logarithms. And the third one is by using a standard graph overshoot versus damping ratio. And on top of that, beside the root locus, I also plot the time response, which is the closed loop time response without controller, but assuming k is equal to 1. And we observe that we have issues here, okay, which is the steady state error, okay. The steady state error is big, which is the input is 1, final value is 0.0204. Okay, so we have issues here, a big steady state error, and the response transient, okay, the curve that's trying to catching up and to get the stable response at the steady state is very slow, which considered as 3 seconds is very slow. So we have to do something, right, in order to make it faster, and by using this approach where we calculate the value of K, which is the intersections between the root locus and the damping ratio line. So the damping ratio line is here, 0.591 is over here, okay? So it is 0.591 is about 0.6. I think the The angle is about 53, if I'm not mistaken. Okay, 53 degrees. Okay, so our concern now is to find this value, the dominant pole value. We call it as the dominant pole. Dominant pole value. Okay, which is by computer, we will get minus 2.03 plus minus 2.77 J. Okay, so the real value is minus 2.03 and the imaginary value is J 2.77. But in the test or in the quiz or in fact in the final exam, we don't have the facilities of laptop or even handphone. Okay, so what they will give you is the real scale plot of the root locus, and you have to use the protector, okay, to measure the 53 degrees. Okay, this protector is available in the trigonometry box. Okay, so you have to print out this one, print out the questions, and then you use this protector to get the 53 degrees and to get the cross-section point to find the dominant pole. Okay, if you get the dominant pole minus 2 plus minus 2.70 is okay. No worries about it as long as the numbers is logical and can acceptable. But if your dominant pole, the intersection point is minus 20 plus minus J27, of course your answer is wrong, okay? Because it's too big, right? And then the next step is K value. So once you get the dominant pole here, so you use this point as the test point, then you calculate the L1, L2, and L3, okay? That is, you get the, what do you call that? Using a theorem Pythagoras, then you will get K is equal to 46, okay? So far, any question on this? Any questions? Ada soalan? Clear?
Okay.
All right, okay. If clear, so we move to the next step, which is the next question. What is the next question? Estimate the settling time, the peak time, the rise time, the steady state error for the value of K in B. So you have to use the, what do you call that? The formula in order to do that. So let me share with you with the iPad. Okay. Oops. Okay. So that. Okay. So you already get the K is 46, right? Again at this operating point here, the dominant pole. Okay. And then we know that in the S-plane, okay, this is S-plane. Okay. So we have the dominant pole over here, which is -2 and J 2.77. Okay. Right. So I would like to remind all of you because this one is a real part. Okay. This is a real part. And this is the imaginary part. Okay. So I call this as a real part, real, real. And this one is imaginary. Okay. And omega D can be defined can be defined as omega n 1 minus zeta square. So what is the difference between omega d and omega n? Telpel-Gil. Do you have any idea what is the difference between omega d and omega n?
Omega n is natural frequency of the undamped, and omega d is I'm not sure about omega d. Omega n is a natural frequency of the undamped response, but not sure omega d.
Already learned.
Is it a damped response?
I'm not sure. So we asked our next brother, Ho Zheng Han. What is the difference between omega d and omega n?
Omega d is, I think it's like damping frequency. And omega n is a natural frequency.
The answer is ho. I'm afraid your answer is wrong.
Okay.
Lo Zhaotian. What is the difference between omega d and omega n?
Not sure.
Okay lah, teruk lah you all ni. Hey, okay, Nurliana Izzati. What is the difference between omega n and omega d? Yana datang eh?
No idea, sir.
Huh? So let me answer for it. So omega d is a damped natural frequency. Omega n is undamped natural frequency. Okay? Boleh? Both are damped. One is damped, one is undamped, right? Can you take note, please? Right, so delete this one. Okay. So we know that on the S-plane, we have the real part and imaginary part. So this one, the imaginary part is the damped natural frequency. The real part is undamped natural frequency. So the value is 2.03 and 2.77. So we use the formula for the second order, which is Ts is equal to 4 zeta omega n. And zeta omega n is the real part. So we take the modulus of real, which is minus 2.03. Then we take modulus, we will get 2.03 positive. Then 4 divided by 2.03, we get 1.97 second. Then for peak time, which is pi divided by imaginary, pi divided by omega d, pi divided by omega n 1 minus zeta square, pi divided by 2.77 from the graph and from the computer information. So you get 1.13 second approximately. Okay. And then from here, we know that zeta omega n is equal to 2.03. Okay, so omega n is equal to 2.03 divided by 0.591. So the answer is 3.43 radian per second. And then the rising time, omega n is equal to omega n multiplied TR is equal to 1.8346. We are based on this table. Okay, damping ratio, zeta, and normalized rise time. Okay, TR. Okay, which can be found in the normalized book. It's a standard table. Okay, so zeta 0.591 more or less over here. Okay, so the value is 1.8346. Then TR will be 1.8346 divided by 3.43, so 0.53 seconds respectively. Okay, so this is the graph from the standard table that we obtained previously. So the formula is omega n TR rising time equal to 1.76 zeta cubic minus 0.417 zeta square plus 1.039 zeta plus 1. Okay. Okay. So I want to ask you, what is the equation of this curve? Yourself. Okay. Yourself. Yourself.
Yes, doctor.
What is the equation for this graph? This line.
It's exponential.
The equation.
That's the equation. It's rise time damage. It's 1.76 s square minus 0.417
Okay.
theta square.
Okay.
This one is triple. Plus 1.039 zeta plus 1.
Mabruk, Yasha. Your answer is correct. So the equation of this line is,
Allah yabarik fik.
okay. I know you're just guessing, but your guessing today is correct. Right, and then we go to the steady state error. The system type is 0 due to the S power of 0. Or you can see here, this is the open loop transfer function. So when you multiply together these poles, you get S cubic, okay? But in front here is S power of 0. So the system is type 1. Sorry, type 0. Type 0, eh? So E steady state for type 0 is 1 plus Kp. So in order to find Kp in this formula, you have to calculate using a limit formula, which is limit S to 0, K ds. Insert the open loop transfer function ds, which is a K S plus 2, S plus 4, S plus 6. So you already calculate in that point, which is 46, okay, from here. Okay, 46 at this point, okay. So 46 divided by 48, so just insert 0 here, 0 here, 0 here. 2 multiplied by 4, 4, 8, 8 multiplied by 6, 48. So the error is, sorry, the Kp, position error constant, okay? Is 0.96, so you insert 0.96 inside here. So 1 divided by 1 plus 0.96, so the steady state error is 0.51. When K is equal to 46. Then you use that particular gain, 46, then you insert inside, you can see that the transient become faster a little bit compared to the previous one, okay? So this is the closed loop transfer function, which is C divided by R, okay? 46, okay? Over, okay? 1 plus S plus 2, S plus 4, S plus 6 multiplied by multiplied by 46. Okay, so you will get the the time response by injecting 1 volt step. Do you know how to do this? Do you know how to find the plotting for this particular time response? Ni Umar, iPad? You know how to find it?
Find what exactly, doctor?
The closed loop transfer function when K is equal to 46.
Closed loop would be, you want the equation?
Yes, 46
Will be 46 over
cubic.
S squared.
Cubic.
S squared. plus and all of that, and then finally plus 46.
Not square, cubic.
Sorry, cubic.
Plus 48 plus 40.
Yes, plus 48 plus 46.
Berapa?
It will be 94.
Are you sure? People?
Pretty sure, yes.
Sure, huh?
Yes.
Okay. So, kita pakai MATLAB lah nak plot time response. Ingat lagi tak? Do you still remember how to plot it?
Yes.
You want to see the plot?
And yeah.
Okay. I open my MATLAB. So S is equal to EF closed loop transfer function, that's CLTF. Closed loop transfer function is equal to 46 divided by S cubic 12 S squared (44S) plus 94. Okay. Correct? Okay, and then step CLTF closed loop transfer functions. Okay. So wait, the computer is busy calculating. Okay, now you get the response. Okay, so I share with you this one. You see? Can you see?
Yes, doctor.
Can you see? So if you want to find the grid, so you click right mouse, grid, okay, and then you want to find the characteristic, the peak response, click right, go to the characteristic, there you go. Okay. Settling time, over there you go. Rise time, over here, there you go. And lastly is the steady state. There you go. Okay. Ibrahim Hassan.
Yes, doctor.
From the closed loop transfer function with the gain k is equal to 46, we obtain this response. What is the rise time from the graph?
0.589 seconds.
Mabruk.
Thank you.
Muhammad Adam Mazlan. Muhammad
Yes,
Adam Mazlan.
Yes.
From the plotting time closed loop time response, what is the peak amplitude?
The amplitude 0.533
volt. 0.533 volt.
Oh,
Bukan volt.
volt.
And what is the overshoot value?
Overshoot 8.97%.
And what is the peak time?
Peak time 1.29 second.
Okay. Sadinan Sakib.
Yes, doctor.
What is the value of the settling time?
It's 1.86 second.
Nur Aina Shafika.
Yes, doctor.
What is the steady state value?
Steady state.
From the graph?
0.5.
Mana ada? Unit dia volt.
0.482.
Huh? 0 point from the graph in your computer. 0 point.
0 point.
What are ini? Aina Nabila? Aina Nabila?
Yes, Doctor. 0.489
Volt.
volt.
Okay. And what is the steady state error? Aina?
Steady state error.
Aina?
Steady state error.
Tak tahu lah tu. Okay, tak tahu. Ada Nur Izzah Hakimah. What is the steady state value?
0.51.
Steady state error. Huh?
0.511.
0.511, which is 1.
1 minus 0.489.
1 minus 0.489 equal to 0.511. Okay. Everybody clear? Everybody clear, brothers?
Yes, doctor.
We move to the next one, which is comparison. So this is what we call a gain adjustment. Or P controller. P stands for proportional. Okay. So we adjust the gain from K is equal to 1 to K is equal to 46. And by assuming the dominant pole at zeta 0.591. Okay. So in reality, what is proportional controller in reality? You use what device?
Tombol.
Tio. What device we use to realize P controller? The gain adjustment. We want to adjust the motor system gain from K equal to 1 to K equal to 46. So what device we use in reality to achieve that?
A knob.
Huh? No idea.
Tombol.
Huh? Come again?
A knob.
A knob?
Yeah.
Knob.
No.
Knob. What is knob? What is inside the knob? What is the behind the knob?
Potentiometer. I don't know.
Huh? Potentiometer. Correct.
Okay, that's nice.
Correct. Your answer is correct. Okay. We use a variable resistor lah. Potentiometer is a variable resistor. Kan? We go to the left, then we turn to the right, turn to the left. Actually, we adjust the gain. Good try. So next example is the third order system, gain adjustment. This time around is we have zeros, okay? At minus 1.5. Then we have the poles at the origin and at minus 1 and at minus 10. Okay, consider the system shown in figure 8.1. Design the value gain of K. Okay, gain P controller lah. To yield a 1.52% overshoot. Okay, spec design. Okay, also estimate the settling time, peak time, and steady state error. Jadi dia punya spec, the spec design is overshoot 1.52%. Spec design, specification. Spec stands for specification, the detail. So only one. It can be 2, it can be 3, or it can be 4. From 1.52%, we will obtain zeta. Am I right? Okay. So 1.52% overshoot will yield zeta 0.8. How we get 0.8? 3 approach. First, using overshoot percentage formula. Second is using zeta formula with natural logarithm. Third is using standard what? Standard graph. Okay.
Doctor, what's the second one again? The name of it?
The name of the second formula, zeta with natural logarithm.
Thank you, Doctor.
Zeta with natural logarithm. What is the equation of this line? Muhammad Muatasim.
Sorry, sir. Come again.
What is the equation of this line?
Exponent negative.
La hawla wa la quwwata illa billah. Usama Bilhaj. What is the equation of this line?
Is it the first one?
First one, yes. This one. Okay. Equation is, this is the y-axis, this is the x-axis. Okay. So overshoot is equal to exponent minus pi zeta over 1 minus zeta square multiplied by 100. So we plot is the third order system with 1 zeros. So how many root locus paths from the plot?
3.
Zaidi. How many root locus paths? Red, blue, green. Red, blue, green. Alisha. Tak datang eh? Okay.
Root locus path because of the power, the highest power of denominator is as power of 3.
So how many?
3 root locus path.
Okay, thank you. So the arrow. So I use blue. So blue is here, blue's here, blue's here. Red, blue's here, blue's here. Green. Can you see the color in your computer? Can you see? Can you see?
Yes.
Yes.
Okay, the arrow. And this one ended at infinity. And this one also infinity. But the blue one ended at 0. Okay. Understand, eh? So 0.8 is the damping ratio line due to the overshoot 1.52% that we get from the graph or from the formula. Then we draw the line, the straight line, which is zeta 0.8, and now it crossed to 3 points at the root locus. This is the first one at K 7.36, at K 12.79, and at K 39.64. Right? cross 3 times. So we have a 3 pair closed loop poles. Okay. We have a 3 pair closed loop poles, and by using the formula of the settling time, peak time, the K, and the steady state error, so we can construct the timetable. Okay, timetable, which is shown here. So this is the first dominant pole, second dominant pole, and third dominant pole, right? With the different gain. Okay, 0 still the same. And then the third closed loop pulse is here. Okay, and the settling time and the peak time and KV. KV, KV. Okay. Why KV? Because the system is type 1. Okay. The system is type 1. That's why we have to calculate the steady state error using KV. Okay. Why type 1? Because this one. This one. Okay. S power of 1. So that's why is the type 1. So type 1 is ESS is equal to 1 over KV. It's not KP, KV. Okay. Right, guys. So the conclusion, the root locus allow us to choose a proper gain, okay, to meet the transient response specification, which is the overshoot percentage and zeta. As the gain varied, we move through different region of response. However, we are limited to those response that exist along the root locus. So this is the disadvantage of using the gain adjustment. So in order to do that, we have to improve it, okay, the system response, okay, by using the flexibility, okay, in the design, which can be increased if we can design for response that are not on the root locus by considering the desired trend response defined by the overshoot percentage and the settling time. With gain adjustment, we can only obtain settling time at A to satisfy the desired overshoot percentage. Point B cannot be on the root locus with the gain adjustment. So that's why we need a controller or a compensator in order to achieve at poles at B. Okay. So therefore, we have to use a compensator, okay, to improve the steady state error. Just now, the steady state error mentioned by our student is 0.5 something in example 1.1. So in order to do that, we have to improve the steady state error using a PI controller, okay? So I stop here for a while. We have a break, about 10 minutes break, okay? Is it okay?
Okay, doctor.
10 minutes break. Okay, can we continue?
Yes, doctor.
Okay. So as I told you before, we already looked at the gain adjustment, or we call it as a P controller or proportional controller, which have some advantage and disadvantage. The advantage is the transient response become faster, okay, when we increase the gain of the system, but it also improves steady state error, okay, from 0.9 something to 0.5 something, but cannot settle down or improve 100% error to zero. Okay, so by increasing the gain, the ESS reduce, but the overshoot increase. Okay, so it will increase the overshoot. Okay, the overshoot is too high. Okay, by reducing the gain, overshoot reduce, but steady state error increases. So there are a give and take. Okay, when high gain, low gain. Capacitors can be designed, okay, to meet the transient response and steady state error simultaneously, okay, by using configurations. Okay, we have two configurations of the controller, which is the cascade compensations and feedback compensations, where in cascade compensation, the compensation network is placed cascade with the plant, and for the feedback compensation, we put the compensator at the feedback path, okay, like this. Okay, so in our syllabus, in our subject, we will focus on this, where the controller will be cascaded to the system, which is the plant. Okay, so both methods change the open loop poles and zeros, thus creating a new locus that goes through the desired closed loop pole locations. So in order to do that, to improve the steady state error from finite value to zero, okay, so we have to use a proportional, integral, or PI controller. Okay, we call it as a PI controller or PI compensator, which is to improve the steady state error. Steady state error can be improved by placing an open loop pole at the origin, as this is increase the system type by 1. Okay, so meaning that when you have a S-plane there, so you put a open loop pole at the origin, like this. So this one is equal to 1 over S. Okay. So as I told you before, we have a type 0, type 1, and type 2. It's based on the denominator single S. If S0, type 0, if S is equal to 1, type 1, and if S is equal to 2, we call it as a type 2. And we have several input for steady state error, which is a step, ramp, and parabola. Okay, so for steady state error, step 1 over 1 plus Kp. For ramp, 1 over Kv. For parabola, 1 over Ka. And for error, for type 0, usually ESS is 1 over 1 plus Kp. And for type 1, 1 over Kv. And for type 2 is 1 over Ka. Okay, as we learned in the control 1, modeling and simulations. Kp, Kv, Ka is a constant, or specifically known as static error constant and system time. Okay, so steady state error, performance specifications, we call it as static error constants, which is a position constant Kp, velocity constant Kv, and acceleration constant Ka. Okay, with the formula limit S to 0 GS, SGS, and S square GS respectively. So PI controller, okay, the concept is shown here. Consider a system operating at a desirable response with a closed loop pole at A. Okay, so this is the A, the operating point. Okay, by adding a pole to increase the system type. Okay, so A is no longer a closed loop pole. Okay, meaning that we add here. Okay, A is no longer a closed loop pole when we add 1/S, okay, to the system. To solve, a 0 close to the poles at the origin has to be added. Thus, A now is a a closed loop pole. So we have to improve the steady state error without affecting the transient response. This is known as PI controller or compensator, which is K multiplied S plus A divided by S. Okay. So now you get the zeros here, and the poles are very near together. Okay, very near together to perform as a PI controller. Example. So you are given example 2, where the damping ratio zeta 0.174. Okay. So you have to prove that by using a PI controller or compensator, it will reduce steady state error to 0. Okay. ESS to 0 for a unit step input without affecting the transient response. Okay. So we have two figures here. The first figure is before compensations, which is feedback block diagram with a plan given by 1/S plus 1, S plus 2, and S plus 10. The poles is here, okay, poles. So after compensations, we apply PI controller. So this is what I call a PI controller, where we add poles at the origin, okay, and zeros at minus 0.1. So you can see that the concept is we allocate, okay, the zeros and the poles, okay, near together, okay. So this is the poles at the origin, and the zeros is very near, okay, which is here, and 0. So you can see that the zeros at minus 0.1 is very near to the added poles at the origin. They're very near. And when the poles and 0 is very near, there is a what do you call that, concept of cancellations. Okay, the poles will cancel the added poles at the origin. Okay, it means that we don't do nothing to the system, but we increase the system type from 0 to 1. Okay, when we add 1/S, which is poles at the origin. Okay, so that is the PI controller concept, right? So in that case, so when we look at this, we plot the root locus here. Okay, so these root locus have 3 paths, right? When we plot it, so is here -1, -2, and -10 is the open loop poles. Then we draw, we have a 3 root locus path ended at infinity. Okay. Then we are given a zeta 0.174 here. Okay. So we draw the zeta 0.74, and the theta is equal to 80 degrees, okay? So when we draw the straight line of zeta, it crosses the root locus at this point, okay? Minus 0.694 plus J 3.926, okay? With the gain K 164.6, okay? And this dominant poles, okay, the equation is here, okay? So this is referred to the S square plus 2 zeta omega ns plus omega n square equal to 0. So for a damping ratio 0.174, dominant poles are here from the root locus, and the gain is K164.6. Okay, so all are done using calculations. The third pole is minus 11.61, okay, which is far away from the imaginary axis and far away from a dominant pole. So that's why we can apply a second order approximation is valid, because the ratio is more than 5. So let's see, this is the ratio. We calculate the ratio. Third pole is minus 11.61 divided by 0.694. How much? Somebody press calculator. 11.61 divided by 0.694.
18.
Huh?
I got 16.729.
16.729.
16.
16.729.
Okay, which is greater than 5. So when the ratio is greater than 5, second order approximation is valid. Okay, so we can use all the formula that is related to second order. Okay, right. So how we calculate the K, the gain K, which is 164.6. Here you are, the length L1, L2, and L3. Okay, so you use the length as I teach you before. Okay. Okay, which is L1, L2, and L3, then we get 164.7. So how to calculate the third pole? Okay, so gain for the third pole is the same with the gain of the dominant pole, which is 165. Okay, so therefore, you have to use the trial and error from the gain at the dominant pole, which is minus 0.694, 3.62 by using the calculator. Okay, so we assume T as the third pole. So S plus T plus S square plus 1.38. This is zeta omega n, and this is omega n square. Okay, so you use this equation, then you use this one as 164. Sorry, 164. Okay, 164 or 165 is the same. And then you solve for T. Okay, so solve for T, you get minus 11.6. This is the method to calculate the third pole. All right, so we plot it. Okay, so we plot, so we obtain this dominant pole, we obtain this third pole. Okay, with the gain 165, 166. Okay, this is the way we calculate the third pole. Then we start the PI controller by adding a pole and zeros at the origin. Okay, adding a pole at the origin and 0 at minus 0.1, which is very near. Can you see? Here. Nampak? Can you see? The zeros minus 0.1 and the poles at 0 is like overlap to each other, very near together. Okay, with the same damping ratio, okay, which is zeta 0.174, we obtain the dominant pole 0.678 plus minus J 3.83 with the gain 158.2. Okay, when we redraw the root locus, we have to redraw after we insert the S plus 0.1 divided by S. Okay. Composite closed loop poles and gain are approximately the same as the uncompensated system. Both give the same transient response. Okay. However, with PI system, is type 1 already, so the steady state error is equal to 0. Okay, so this is the open loop transfer function before PI controller. So after you add a PI controller, which is GC, here S plus 0.1 divided by S, multiply the open loop transfer functions. Okay, now the system is type 1. Previously, type 0. After you use PI controller, cascaded, you multiply, you get type 1. Okay. So when the type 1, we plot again, we verified, yes, it's correct. It didn't affect the transient response. The dominant pole still almost the same, the gain almost the same. Okay. So, but when we compare the transient response, this is before. Okay, so you have a steady state value there, 0.892. And the steady state is 1 minus 0.892. How much? Berapa?
0.108.
0.108. And after we apply PI controller by adding zeros, by adding poles at the origin and zeros at minus 0.1, we calculate the time response, then we obtain the steady state value equal to 1. So ESS is equal to input 1 minus steady state value 1 equal to Abu Lata, equal to
0.
Sifar. Okay, equal to Sifar or 0, right? So when we superimpose the graph, so the black one is the uncompensated before design, and the blue one is the after design. Okay, and the input is 1 volt. Any question? Any question? If no question, so the general transfer function of PI controller is given by this. GPI KP plus KI divided by S. Okay, so K is equal to S plus Z divided by S. Okay, so Z is the zeros lah. Just now, which is minus 0.1. And this is the poles at the origin. Okay, so this is the block diagram for PI controller, which is P and I. So P and I consolidate, gabungkan, unite, it become PI controller. So PI controller is designed by adding a pole and the origin at 0 at S minus Z. So if you want to choose other than that, minus 0.01 also okay. Minus 0.2 also okay. Minus 0.001 also okay, as long as it is close to the origin. So the value of 0 can be adjusted by varying Kp divided by Ki divided by Kp. So if the same transient response as the uncompensated system is required, choose the 0 close to the origin. This is the important word. Choose the 0 close to the origin, for example, minus 0.1 or minus 0.01, okay, in order to obtain the PI controller. Example 2.1. Imran Hakimi. Imran Hakimi.
Yes, Doctor.
Can you read the question?
For the unity feedback system with open loop transfer function, design a PI controller to achieve a transient response as the following: overshoot 10%, settling time 3.2 seconds, ESS 0 ESS, and verify the design using MATLAB.
Okay. So now the system type. What is the system type? Nur Aina Shafiqah. What is the system type? Tak ada. Nurliana Izzati.
System type 0.
Okay. Type 0. So design a PI controller. So okay. So this is what do you call that, second order system kan? We plot we plot the time response. Okay. So this is open loop. Find the closed loop. Okay. So the input is 1, steady state 0.778. Steady state error dia berapa? Nurliana Izzati. What is the steady state error? From the graph given. Tak datang. Datang ni, ramai tak datang.
0.222.
0.222. 0.222. Eh?
Yes.
So we have a steady state problem. Then we plot. Okay. So since the system is a second order system and the number of root locus is 2. Okay. So we have two lines here. One is the blue line. Root locus start from the poles ended at infinity. Okay. And this is what point? Just asking. Okay. This one. Muhammad Adam. Adam.
Yes, itu.
Point merah ni is what point?
Origin.
Origin kat sini lah bang. Ayo.
Sorry.
Allah. Astaghfirullah.
Merah tu
DP.
Damping 0.59.
Astaghfirullah. Dah sudah, jangan mengarut. Abdul Ghani side, what is this point? Abdul Ghani side. Okay. So you absent. Muhammad Khalid. Muhammad Khalid.
Yes, doctor.
What is this point? The name of this point?
This one is a breakaway point.
Breakaway point. Mabruk ya Syekh. Breakaway point. Estimation values. Estimation values. Khalid.
Yes, doctor.
Estimate the values
Of the breakaway point. 0.
1.25, doctor.
1.25 lah. Oh, it's between 1 and 1.5. Syekh. Syekh Khalid.
Yes, doctor. So
It's between 1 and 1.5. This is 0. Astaghfirullah. So it is 1.25. Okay, so I think your basic is very wrong. So I remind you, the quiz will be on the 8th of April. 8 April, 8th of April. 9 p.m. local time, Malaysia. So what is the time at Saudi Arabia? 9 p.m. Arab brothers? Any from KSA?
4 p.m.
Huh? 4?
Yes, 4 p.m.
Who is that?
It's me, but I'm here in Malaysia.
Malaysia. Is there anybody in KSA in the class? No. Okay. Egypt. What time in Egypt? 9 p.m. 9 p.m. local time, Malaysia.
It's 3 o'clock.
Huh?
3 o'clock.
3 o'clock. 3
p.m.
3 p.m.
Yeah.
The quiz will be 9 p.m. local time, 20 minutes from 9 to 9:20. 10 questions. Okay. Are you aware about it? Okay. Okay. So KP is 3.5 by using the calculations, which is here. The intersection point between the zeta 0.59 line to the rule locus is 3.5. Sorry, the gain at the poles is 3.5. So you use this value inside the formula. KP 3.5. ESS is equal to 0.22. Sketch the rule locus, the system without a PI controller, the first step. Find the closed loop poles for the required transient response, which is this one, dominant pole, minus 1.25 plus J 1.71 to achieve 0 ESS and add pole at the origin, which is here using the PI controller, add inside the GS, okay, resketch again, system with the PI controller, then we get the same transient response with the 0 steady state error. Okay, so this is the calculation of it. Okay, so when we apply, we draw again the rule locus with the PI controller, we obtain the settling time 3.2 seconds. So KP is equal to infinity because we already increased the system type from 0 to 1. Then ESS 1 over 1 plus infinity, which is equal to 0. Okay, khalas. Previous error 0.222, 0.222. Now ESS SIFA. Any questions? Is there any questions? Okay, so we get the without controller, with controller, okay, and compare it. Okay, so we get the 0 steady state error. Any questions?
Doctor, the rising time and the steady state time, all of that still the same before and after compensation. Okay. Just the error changes.
Okay, we see this one with and without PI controller. Okay. This one is without. Okay. Without PI. So error 0,222. Okay. This one with PI controller. Okay. So the steady state value is 1. 1 minus 1. You can see that this one, because if we zoom this point. So we get this one. Okay. So you compare with the top one. Okay. A little bit slower, but the error is 0 because we want the spec design is we want the error become 0. Okay. We maintain the transient response. A little bit change, no problem, as long as the steady state error is 0. Actually, we do nothing when we do the PI controller because the pose at the origin, okay, and then we add 0, which is near, pose at the origin, then we put the zeros very near, okay, 0 and minus 0.1. 0 and minus 0.1 is very near together, am I right? Are you agree with me?
Yes.
It seems that we cancel each other, okay? We cancel each other. But at the same time, we maintain the transient response specification, and the important thing, the error from finite value 0.322 becomes 0 when we apply PI control.
Okay. Okay, thank you, doctor.
I hope you understand. It's very difficult to be a lecturer, okay? Teach people, to make people understand. Okay, so that is my job, to bring all of you on the straight line of control system design. Siratal mustaqim. Ihdinas siratal mustaqim. Huh? Okay?
Okay, thank you.
Okay. Any questions? It's 12:30. It's lunchtime. Ta'am, Sefan, Shuru Shapadam, Telpel. Any question?
So far, no, I think I have to review the recorded session.
Okay, I understand. Okay.
Doctor, regarding the quiz on the 8th, right? How many questions is it?
Okay, I repeat again. The quiz 1, scope chapter 1, root locus, not chapter 2, chapter 1, on root locus theory. The date is 8 April. 8 April. In Arab, 8 is what? Ahad, Isnin, Selasa,
Samania.
Arba'ah, Samaniyah.
Yes.
April, 9 p.m. local time Malaysia. Okay, started 9 p.m. ended 9:20. Is objective question. 10 objective question. All the answers are very near together. Okay, very close answers. So it's objective. You click, then you submit. Then the computer will calculate for you the quiz marks. Anta fahimta? You understand?
Yes, doctor.
Liana, Nuliana, berapa bulan quiz?
8.
8 apa?
8 April.
Pukul berapa?
Pukul 9.
Sampai?
9:20.
Lama Adrian, Justin? Adrian? Adrian, Justin?
Hello.
Ababa?
Apa boleh dengar? Tak terdengar. Hello.
What is the scope for quiz 1?
Root locus.
Locus, chapter 1.
Yes.
Azira Ahmad. Azira.
Yes, saya.
How many questions quiz 1?
10 question.
10 questions. Answer how many questions?
Every?
Answer all questions.
Yeah, answer all question.
Nur Izzah Hakimah.
Yes, doctor.
Break-in point and breakaway point. What is the difference? Break-in point and break.
Break-in point, arrow masuk.
Break-in point occurred between two
poles.
Two zeros. Breakaway point occurred between two
Zeros.
poles. Astaghfirullahalazim. Okay lah. You have a break. Then you see my YouTube. Then you see my slide, my book chapter, YouTube. Okay, so make sure you prepare on Thursday. I will ask again the question on Wednesday. Okay. Okay, brother. Okay, sister.
Okay, doctor.
Now you have a lunch. Okay. Go and have a lunch. Okay. Then you study again.
Doctor, the quiz time duration is 9 p.m. to 9:20 p.m., right?
To 9:20, 20 minutes only.
Okay. Thank you.
Thank you, doctor.
Okay. Subhanallahi wa bihamdihi, subhanallahi wa bihamdika, asyhadu an la ilaha illa anta, astaghfiruka. Thank you and see you on Wednesday. Assalamualaikum.
Waalaikumsalam. Thank you.
Waalaikumsalam.
Thank you, Doctor.